Okay, guys, so I want to talk about an object rolling without slipping versus an object that slides down an incline with little to no friction, and kind of compare the two in terms of energy now that we've talked about moment of inertia. So on the left-hand side, we have an object, let's say it's round, and it's rolling down the incline, and let's say that it rolls without slipping. I think my pen's on. Rolls without slipping. Whereas this one is going to slide, and let's assume no friction for now. Okay, so what we learned is that when an object rotates, it has, in addition to translational kinetic energy, if it's, moving its center of mass, it also has rotational kinetic energy. So at the top of the incline here, if the incline has a height h, then the object has a potential energy of mgh. When it gets to the bottom, all of that energy is going to turn into kinetic energy, but it's going to be in two forms. It's going to be in translational kinetic energy, which we've seen as 1/2 mv squared, and it's also going to be in rotational form, which is 1/2 I omega squared, which we just started seeing. So what we learned is that this I term, the moment of inertia, it depends on the distribution of mass and the shape and all of that. But if you looked at, the different values for the moment of inertia for different round objects that are rolling, you find that the I value is usually some coefficient times mr squared. So I'm just going to call, for now, just to be generic, let's call the coefficient n, the letter n, and let's plug that in. So what we get is this, the coefficient n times mr squared, and then omega squared, if we're rolling without slipping, omega could be written as v over r. So omega squared could be v squared over r squared. Okay. So let's clean that up. We have an m in every term in this expression. So we can cancel those out. We also have r squared over in this parentheses, and r squared in the denominator right on the outside. They're going to cancel each other out. There. So we get 1/2 v squared plus 1/2 n v squared. If we factor out 1/2 v squared, we get 1 for the first term and n for the second term. Okay, so I can multiply both sides by 2 and get this. And then I can solve this for v. So I divide by 1 plus n. Or we could write it this way. So that's going to be an important result. Let's hold on to it for a minute. And let's look at that compared to the object that slides. So if it's sliding, it's not rotating at all. It doesn't have rotational kinetic energy, only translational. So we could say mh equals, whoops, didn't mean to hit that, 1/2 mv squared. If there's no friction, all the potential energy turns into kinetic. Cancel the m's, solve for v, and we get this. So take a look at that result compared to the result we got earlier for the rotating object. You'll notice they're similar but not exactly the same. The one on the right is root 2gh over 1. The one on the left is root 2gh over 1 plus n. So here's an important result. An object that slides down an incline with no friction is always going to be faster than an object that rotates. Think about why in terms of energy. The object that rotates has to use some of its energy, some of its stored potential energy to spin, which means it's going to have less available to actually translate, to actually move its center of mass down the incline. Whereas the object that's sliding turns all of its potential energy into translational motion. So it's going to go faster, assuming there's no friction, okay, for the sliding object. If there were friction, we would have to take that into account, and then it would be a harder question to determine. But any object that can slide without friction will always beat an object that rolls and has to rotate. Also, take a look at the result on the left side. This kind of goes back to the lab that we did. If you look at the expression, v equals root 2gh over 1 plus n, what it shows is that the only thing that actually affects the speed at the bottom is the height of the incline and this n value, this coefficient. So if you remember in the lab that we did, we had objects of all different sizes, all different radii, all different masses. It turns out that if we want to know the speed at the bottom does not depend on the mass. It does not depend on the radius. It just depends on n, which has to do with like the shape and the mass distribution and things like that. Now, this is not to say that those things like mass and radius, I'm not saying that they don't affect the rotational inertia. They do. A bigger, more massive object or an object with a bigger radius is going to have a bigger rotational inertia than a smaller object. But a bigger, more massive object also has more stored potential energy to start the whole motion in the first place. So those two things kind of balance each other out, and you get the same speed at the bottom. Really all it depends on is the mass distribution and the shape. So this is an important result, and if we know what that coefficient n is, we can figure out which objects are fastest. So in the textbook and AP questions, there's always questions about, which of these objects would make it to the bottom of a hill first. So all we have to really do is say, well, are they sliding or are they rolling? And then we have to look at, okay, well, if they're rolling, what's their mass distribution look like? Is it solid or is it hollow? Is it spherical or is it cylindrical? And kind of take it from there, and then we can figure out how fast it's going to go.